Okay, good morning. So, this is our 30th lecture. In the previous lecture, we completed discussion on differential form of governing equations. Today, we will be talking about unsteady wave motions. So, basically, if we see our previous cases, so previously we discussed three important topics. First one was the flow across normal shock waves, second was flow across oblique shock waves, and third one was internal flow through ducts, whereas we were having variable area geometries. In all these three cases, we have specifically discussed the case of a stationary wave. So, when we are having the stationary wave, then actually our flow situation is more simplified, and this type of situation mainly occurs in case of steady flow scenarios. If our situation is of unsteady flow, then we will not be able to analyze our situation exactly by considering the stationary wave situations, and we have to consider actually moving waves in our analysis. Okay, so typical example, if we see in reality actually waves are kind of always moving. Okay, but we try to change the frame of reference and we try to analyze the situations in such a system, so that actually we can see a wave as nothing but a stationary one, so that flow situation can be easily analyzed. So this can be understood with the help of a simple example. If you think that we have an aeroplane, okay, so say this is the aerofoil structure of an aeroplane, and say the flow situation is such that you are having formation of some shock wave over here. So if you will be finding, say, shock wave is forming something like this. So now you will be finding that ultimately what happens, basically in our ambient air is stationary, so ambient fluid is stationary, and uh, what is basically happening, this particular whole structure is moving with some velocity. So as it is moving with the velocity, the wave which is adhered to this particular structure, this wave is also moving at the same velocity. So now if you consider a person, say he is standing on ground, okay, so person standing on ground will see that this particular surrounding fluid is stationary, and this wave, this aeroplane is actually moving. It is going away from the, say, person where he is standing, or approaching towards him depending upon the location of the aeroplane. So he will be he or she will be experiencing that this particular aeroplane is actually moving, and when the aeroplane is moving, shock wave is also actually moving with the same velocity. So that is something which is the real situation. However, this situation can be simplified. Now what I can do, I can just take this person from the ground and put him inside the plane itself. So when a person is actually sitting on the moving object, so he or she will see that, experience that shock wave is actually stationary with reference to him or her. Okay, so then any observer who is sitting on the plane, so which is actually moving, and shock wave is also moving at the same velocity with the plane, so that particular observer will find that our shock wave is nothing but a stationary wave, and our surrounding fluid is actually moving. And this is typically another way of looking into this problem. Third perspective can be, say, one can say that, okay, before the aeroplane is actually going into flight, uh, one wants to do its complete testing in a wind tunnel itself. So say one develops a huge supersonic wind tunnel such that the whole aeroplane can be put inside that wind tunnel. Now the aeroplane will be a fixed object inside the wind tunnel, and flow of the fluid is actually moving. Okay, so flow is moving, and corresponding to that also there will be formation of a shock wave, but with reference to the laboratory. Okay, so the laboratory in which that wind tunnel is situated, with reference to that laboratory we will be finding plane and shock wave are stationary, but fluid is now actually moving. Okay, so there are different perspectives to look into the same situation. So till now whatever analysis we have done, there our major perspective was the last one what just now I have explained to you. So say we are considering kind of a wind tunnel situation where we have a a fixed object, and then flow is happening over the object, and then at a fixed location there is formation of a shock wave which is not moving with reference to the laboratory setup. Okay, so that is something which we have considered till this point. Now this type of situation is not always possible, or cannot be always applicable for all the type of physical situations. Therefore we have to somehow account for the motion of the unsteady waves. Okay, so it means the meaning of unsteady is that time dependent motion of the waves. So let's try to see one situation. So what I can do, I can have first situation whatever we have done earlier. So we used to consider that we were having a fixed shock wave. So this is nothing but a fixed shock wave, and say flow is from left to right. Okay, so this is point number 1, this is point number 2. So one is upstream of the shock wave. So say here velocity is v1, and this is downstream of the shock wave where velocity is v2, and our shock wave is actually stationary. Second situation, as I told you, that we can have is we are having a shock wave but it is not fixed. Say this shock wave is moving with certain velocity w towards the right. Okay, and in the right side we have nothing but our stagnant fluid. Okay, so here we are having stagnant fluid. So when shock wave is moving, say this is at some time t1, so at after some time delta t, at other time t2, this wave will be somewhere over here. So now whatever the stagnant fluid was there, obviously when wave is moving, that wave will impart certain motion to this stagnant fluid. Okay, so that is something which we will be experiencing, that when wave is moving through some fluid, we will be finding that the fluid behind the wave will also have some sort of motion. Okay, so that type of motion is referred to as mass motion. So basically when a wave travels through a flow field, it introduces certain mass motion to the fluid medium. Okay, so when it will be introducing the motion to the fluid medium, so let's say it has given velocity vp to the fluid medium. Okay, so now if you have to analyze this situation, so in first case what was happening, our shock wave was fixed. Okay, and this fluid was moving at velocity v1, and here I was getting velocity v2. Now if I consider, say my situation is such that in stagnant fluid and mass motion I am getting similar set of parameters. So if I am getting similar set of thermodynamic property variations, in that case I can say that I can have a shock wave of almost the same strength. Okay, and the velocity of the shock wave w can be made equal to that of velocity of this, yes, the upstream fluid which was moving. Okay, so and so I can consider that wave is moving to this stagnant fluid with velocity equal to v1. So in that case what will be happening, when this wave will be moving, it will be imparting certain velocity to the fluid through which actually it has passed, and this fluid will also be having tendency to move with velocity vp towards the wave side only. Okay, so this fluid will also tend to move in the direction of the wave only. So that is something which happens. And for certain set of cases, what we can do, we can analyze this situation, the second situation, by using the assumption of first situation only. As I explained you, in case of an aeroplane, what I can do, I can place the observer on the aeroplane itself. So with reference to him, shock wave can become stationary and fluid can be moving. Okay. But as I told you, that there are certain set of applications for which actually we cannot purely go with the this type of stationary wave analysis, and we have to consider the transient or unsteady wave motions. So one such example is very popular device which is called as shock tube. Okay, so shock tube is a very popular device, and this particular device is used for determining the properties, I should write thermodynamic and chemical properties of gases at high pressures and temperatures. Thermodynamic and chemical properties at extremely high pressures and temperatures. Okay, so this is called as a shock tube. So typically if you see a shock tube, you will be finding a tube of, say, fixed cross section, something like this, and in this tube, here, say, initially I have some diaphragm. Okay, and here I am having certain properties. Say these are indicated by, this is indicated by region 4 and this is indicated by region 1. Say here pressure is P4 and this is greater than P1. So here pressure is P1. Okay, so what we have done, we have two compartments. In one compartment we are having a gas at low pressure P1, and in other compartment we have a gas at higher pressure uh, P4, which is greater than P1. Okay, now in this type of situation, if I break the diaphragm, obviously I have a pressure difference. So because of that pressure difference, I will be finding certain wave motions over here. So particularly in this type of situation, the section which is having high pressure, that is called as driver section, and the section which is having low pressure, this is called as driven section. And typically my initial pressure profile is, if I have to plot pressure as function of length of this shock tube, so in this region my pressure is P4, okay, up to this point. Then here I have sudden decrease of pressure, and then on the other side of compartment I have pressure as equal to P1. So this is my initial pressure profile of this particular shock tube. Okay. Now if you see, now what we are doing, we are now actually rupturing this diaphragm. So if we rupture the diaphragm, what will be happening? There will be two implications of this. First will be, if I rupture the diaphragm, I will be finding that my shock wave will originate at the diaphragm, and that particular shock wave will keep on traveling towards the driven side. Okay, and another thing, I will be experiencing a series of expansion waves will form, and these expansion waves will move towards the driver side or driving side. Okay, and this motion will keep on continuing. So say this is at some time instance t1. Now if I go to some other time instance t2, I will be finding, say, now my shock wave has reached somewhere over here, okay, and expansion waves are coming towards the further coming towards the uh, driving section. Okay, so ultimately what will be happening in this particular diagram? So any region on the downstream of the shock wave is still not influenced, still is at pressure P1. So say here far away from this, so obviously it will be at 0.1. Here it will be at condition number 4. So what I can do now, if I have to plot the pressure profile, so pressure profile will be something like this. Here pressure profile will become this. Pressure is P4. The pressure in region 1 is P1. Now let's consider that here the region which is just upstream of the shock wave is having state 2. Okay. Another important point is when I have only one dimensional flow, so what I will be finding that when this shock wave is moving, behind the shock wave also it will be imparting certain motion to the stagnant gas, and that stagnant gas will also try to move towards the shock wave. So I will be finding that the fluid in driving section will keep on moving towards the driven side. So I can say that if I want to create the separate identity for fluid in driving section and fluid in driven section, so I can say that in between the driving fluid and driven fluid I will be having some contact surface, okay, which is segregating the identity between driving fluid and driven fluid. Is this point clear? So over here I am referring to identity of the fluid specifically. I am not talking about properties. So more than properties I am talking about identity. So say this is the contact surface between these two, and after some point contact surface is, say, over here. Okay, near the contact surface, say my properties are given by P3. Okay, so contact surface is also now moving towards the shock wave. So ultimately what will happen, up to this shock wave, when I have stagnant fluid, their press up to that point pressure will remain P1 only. At this point I will be having jump of pressure, because when shock wave is passing through certain fluid medium, it will try to increase its thermodynamic property, so it will be having increase in its pressure. So I have some increased pressure, say this is my pressure number, pressure value equal to P2. Okay, then this is the entire fluid medium through which shock wave has passed, so I will keep on coming at the same pressure level, and obviously at contact surface also I will be having pressure equal to P2. So it means I can say P3 is equal to P2. Okay, so just at the contact surface also my pressure will remain the same. But what is happening uh, behind the contact surface? So behind the contact surface in the driving section we will be finding that here basically expansion waves are there, and these are traveling towards the right. So what expansion waves does, expansion waves leads to gradual shift in the pressure, and these will gradually try to decrease the pressure of the driving section. So gradually from P4 to P3 pressure will decrease in the driving section because of the presence of the expansion waves. So this will be my, say, new pressure profile over here, and say this pressure profile is at some time instant T2. Now if I further go to some another time instant T3, Then ultimately what will happen at other time instant t3, say my pressure profile may be something like this. So this blue colored is nothing but at some time t3 which is greater than t2. So by that time my shock wave has reached at this location. So whereas I am having the presence of shock wave, there I will be having actually sharp discontinuity in the pressure, and where I have the presence of series of expansion waves, there I will be finding the smooth uh, smooth transition in my pressure. Okay, so that is something which we are finding over here. So here what is happening basically, when the wave is moving, along with the motion of the wave, my whole set of parameters are also changing with time. So this is nothing but a complete unsteady flow type of situation, and for this unsteady flow type of situation we will not be able to analyze the situation by making the assumption of a stationary shock wave. So for this particular case, if we have to analyze it, we have to consider the case of a moving shock wave only. Okay, is this one clear? Now what we will do, we will try to first make some analogy of stationary shock wave solution with with moving shock wave solution. We will try to create some analogical situation so that majority of our results are applicable in this range also, and then we will see further that how this moving shock waves changes different situations. Okay, so typically if you recall, we considered a situation in our stationary system that we have a normal shock wave, and in upstream direction we have velocity v1, in downstream we have velocity v2. Okay, and typically if you see, your continuity equation was rho1 v1 equal to rho2 v2, then p1 plus rho1 v1 square equal to p2 plus, energy equation was h1 plus v1 square by 2. So these were the governing equations. Okay, and all the relations, normal shock relations, oblique shock relations, we have obtained using these equations, governing equations only. Okay, now typically because we were having the case of a stationary shock wave, so for this typical situation, even with reference to the ground or with reference to laboratory also, we can say that the fluid velocities were v1 and v2 only. But if I change slightly the situation and consider the case of an aeroplane, so for the case of aeroplane, actually my flow is stationary, but shock wave is moving with the aeroplane. Now if I place the observer to the frame of to the uh, aeroplane, then what will be happening, with reference to that observer who is sitting on the aeroplane, he will be finding that shock wave is stationary but fluid is moving. So it means uh, whenever we have done this analysis also, corresponding to this analysis also, our v1 was never the velocity of fluid with reference to ground, because with reference to ground that fluid was stationary even for the case of aeroplane. Okay, but what was happening, v1 was velocity of upstream fluid with reference to normal shock wave. Okay, similarly v2 was velocity of downstream fluid with reference to normal shock wave. So that is something which we have to explicitly understand over here. Okay, so whatever analysis we were presenting, that was not for motion of fluid relative to ground, that was for motion of fluid relative to the shock wave. Okay, because our reference over there was actually shock wave, and because of that only we could easily take the assumption of a stationary shock wave. Okay, so now using the similar analogy, if I try to consider, if I try to deduce the continuity and momentum and energy equation for a moving shock wave, then how we can do that, let's try to see. Now what I want to do, I want to consider that once again I will be having a shock wave, but now this shock wave is not stationary. Okay, it is moving, say, with some velocity W. Now fluid ahead of it is stagnant and fluid behind it is having mass motion. Okay, and this particular mass motion will be having velocity, say, Vp, and towards the shock wave only, and this is region 1, say this is region 2, and here in this region 1 I can say that fluid is stagnant, so V1 is 0. Okay, is this point clear? Now once again if you put your observer on the shock wave, so with reference to the observer you will be experiencing that V1 is equal to W and V2 is equal to W minus Vp. Okay, so now once I place the observer on the shock wave, I am finding that V1 is equal to W and V2 is equal to W minus P. So this gives us interesting finding that we were able to relate our V1 and V2 corresponding to our stationary shock wave case. Okay, so now I can actually write down the continuity and the momentum and energy equations. So continuity equation for this will become rho 1 W equal to rho 2 into W minus Vp. Okay, then P1 plus rho 1 W square equal to P2 plus rho 2 W minus Vp square, and similarly I will be getting H1 plus W square by 2 equal to H2 plus W minus Vp square by 2. So now let me number these equations 1, 2, 3. Now from equation number 1 I can say that W minus Vp is nothing but equal to rho 1 by rho 2 into W. Now let's substitute this particular replacement in equation number 2. So if I do substitute in equation number 2, then my equation number 2 becomes P1 plus rho 1 W square equal to P2 plus rho 1 by rho 2 square. Yes, rho 1 by rho 2 square into W square into rho 2. Okay, so from here I am getting P1 plus rho 1 W square equal to P2 plus rho 1 by rho 2 into rho 1, fine, W square. Okay, now let's segregate the terms involving W. So I can get rho 1 as common, and inside I can get 1 minus rho 1 by rho 2 times of W square is equal to P2 minus P1. Okay, so this further simplifies that W square equal to P2 minus P1 divided by rho 2 minus rho 1, okay, multiplied by rho 2 by rho 1. Okay, so using this equation, I can actually relate my W, the wave velocity, as function of pressures and density. Fine. As now from equation 1, our W minus Vp is equal to rho 1 by rho 2 into W. So square of this, so I can say that W minus Vp square can be equal to rho 1 by rho 2 square into W square, and if I replace W square over here, that will become P2 minus P1 by rho 2 minus rho 1 into, and ultimately it will become rho 1 by rho 2 times upon rho 2 minus rho 1. Okay, so I can say this is, say, my equation number 4, this is equation number 5. So I have derived some relations for W square and W minus Vp square in terms of uh, pressures and densities. Okay, so once I have obtained these relations, now what I can do, I can substitute these two relations into our energy equation. Okay, so if I substitute back this into my energy equation, then energy equation is W square by 2, so that will be becoming 1 by 2 of P2 minus P1 by equal to H2 plus half of rho 1 by rho 2 into P2 minus P1 by rho 2 minus rho 1. Is it correct? Okay. Now, another interesting thing, you can write H is equal to U plus P by rho. Okay, so that if we do, then we will be getting U1 plus P1 by rho 1 plus half of P2 minus P1 by rho 2 minus rho 1 into rho 2 by rho 1 equal to U2 plus P2 by rho 2 plus half of P2 minus P1 by rho 2 minus rho 1 into rho 1 by rho 2. Okay. Now, this is a typical equation. If you recall, earlier we had once derived Huguenot relation, particularly for normal shock waves. So what was in case of Huguenot relation? In case of Huguenot relation, we have completely written our energy equation in terms of thermodynamic property. We made it completely velocity free, okay, Mach number free. So if here this particular equation also we have now made completely velocity or Mach number free, so if we further simplify this equation, it will give me u2 minus u1 equal to p1 plus p2 by 2 into 1 by rho 1 minus 1 by rho 2, and this is equal to, even further simplification will give me specific volume at point 1 minus specific volume at point 2, and this is nothing but identical to that of our Huguenot relation. So now one important point is that one important outcome of this exercise is that Huguenot equation, when we have analyzed Huguenot equation, we have analyzed by considering that our wave is fixed and our fluid was actually moving, and this particular equation, when we have derived, here we have considered that our wave is moving and fluid one side is stagnant, and behind the wave, after actually wave passes through the fluid medium, then it is imparting motion to the fluid, and then we are having movement in the fluid medium. Okay, and that particular situation is able to is producing us nothing but the final form of the equation, exactly the same. Okay, so it means that in some sense our consideration of stationary shock wave for a moving shock wave case is actually true. So it means stationary shock wave analysis is, or even moving shock wave analysis is not far from stationary shock wave analysis. So we are having huge similarities between the two things. Okay, then another important point comes now. What we have to do, basically we have to try to represent the variation of different properties for the case of even moving shock wave as well. Okay, so for that already we have now the governing equations. Once we have governing equations, whatever analysis we have performed for stationary shock wave, we can perform the similar set of analysis, and by doing this analysis, whatever final outcomes we are getting, that I will now show you. I will not go to the repetition of entire mathematical procedure again. Okay, we have already done what if we are having continuity, momentum and energy equations for case one dimensional case, purely one dimensional case of a stationary shock wave. We have done some mathematical analysis, and we have found the final correlation, final relations for variations of properties. But important point is these relations were only possible for, and that analysis were only possible for calorically perfect gas. Okay, so similarly, if we take over here the assumption of calorically perfect gas, that U is equal to CVT, where CV is constant and P is equal to rho RT. So if I invoke these two assumptions in my previous equation, which just now I have got identical to that of a Huguenot relation, if I impose these assumptions, I will be able to find out the variation of properties T2 by T1 and rho 2 by rho 1, etc. Okay, so from this analysis we get T2 by T1 equal to P2 by P1 times gamma plus 1 divided by gamma minus 1 plus P2 by P1 divided by 1 plus gamma plus 1 upon gamma minus 1 into P2 by P1. Okay, so this is one important relation I am getting. Then second important relation is for ratio of densities. So ratio of densities comes out to be 1 plus gamma plus 1 upon gamma minus 1 times P2 by P1 divided by gamma plus 1 upon gamma minus 1 plus P2 by P1. Okay, so typically if you see, when I am calculating the temperature, okay, when I am calculating the ratio of temperatures, that is coming as function of gamma and ratios of pressures P2 by P1. Similarly, when I am calculating rho 2 by rho 1 density ratio, that is also coming as ratio of pressures. So earlier, if you recall, what we have done earlier, we have considered the upstream Mach number. and we have represented all the properties as the function of upstream Mach number. But in the present analysis, because our fluid medium is stagnant, so as fluid medium is stagnant, so flow velocity is equal to 0. Okay, so that is the reason, and we are having a moving shock wave. So for most of the cases, if we have to characterize the strength of the moving shock wave, actually ratio of pressures is an important tool. Okay, so ratio of pressures is kind of considered as an important parameter which which gives us information about the strength of the shock wave. Okay, so as it tells us about the strength of the shock wave, so that's why our majority of properties are actually correlated in terms of P2 by P1. Okay, as our flow is stagnant, but still if we want to make some analogy in terms of Mach number, what we can do, we can define a Mach number which I can call as ms. So ms is nothing but shock wave Mach number. So though our fluid medium 1 is stationary, but still I can define speed of sound in that medium. And what I can do, because I am defining a shock wave Mach number, so I can take the velocity of the shock wave in place of velocity of fluid, and then this I can consider with speed of sound corresponding to the stagnant fluid A1, and with reference to that, what parameter I am defining, that I am calling as ms. Okay, now if I substitute back this definition W by A1 of shock wave into my momentum equation, I will be getting finally a relation in between ms and P2 by P1. Okay, and that relation will be P2 by P1 equal to 1 plus 2 gamma by gamma minus 1 into ms square minus 1. Fine. So what I have done, basically in my momentum equation, I have substituted in place of velocity this Mach number, and then I have applied over there the assumption of calorically perfect gas, and then whatever the speed of sound relations were applicable for calorically perfect gas, these I have substituted, and after doing some algebraic manipulations, we will be able to get P2 by P1 equal to 1 plus 2 gamma by gamma minus 1 ms square minus 1. So from this I can also relate ms, in terms of pressure ratios. So ms from here comes out to be gamma plus 1 upon 2 gamma times P2 by P1 minus 1 plus 1 and square root of the entire thing. Okay, so this is another interesting relation which we have actually obtained from here. Okay, now from continuity equation, we had this relation. From continuity equation, we had this relation rho 1 into W is equal to rho 2 into W minus Vp. Okay, so from here I can make attempts to find the value of Vp. So if I calculate value of Vp from here, what I can do, I can take rho 2 into Vp on other side, and W times rho 2 minus rho 1 on one side. Okay, now I can divide with rho 2, so my Vp will be becoming W times 1 minus rho 1 by rho 2. Okay, so what is now what I can do, uh, the way we used to write down Mach number for the downstream flow, here also I can try to write down the definition of Mach number for the fluid which has undergone through the mass motion. So for that, Vp by A2 I can define. Okay, so this Vp by A2 will become nothing but Vp by A1 into A1 by A2. Now what I have done, I have divided and multiplied with A1. Now for a calorically perfect gas, this A1 by A2 will be becoming square root of T1 by T2. Is this point clear? Because speed of sound is equal to square root of gamma RT, gamma R will cancel out, and I will be getting Vp by A1 into square root of T1 by T2. So just now we have calculated Ms. What is Ms? Shock Mach number. So Ms is nothing but W by A1. Okay, it is W by A1, and I know that Vp by A1 if I have to calculate. So I can write Vp by A1 equal to Vp, just now I have calculated W into 1 minus rho 1 by rho 2. So I can write W by A1 into 1 minus rho 1 by rho 2. So now this first term Vp by A1 I will replace with this quantity. Okay. So W by A1 just now I have calculated square root of gamma plus 1 by 2 gamma into P2 by P1 minus 1 plus 1. So let me make these substitutions. My Vp will become square root of gamma plus 1 by 2 gamma times P2 by P1 minus 1 plus 1 times 1 minus rho 1 by rho 2 and multiplied by square root of T1 by T2. So T2 by T1 I have calculated. So square root of T1 by T2 also I will be easily able to calculate. So let's calculate, let's substitute square root of T1 by T2. So that will be becoming P1 by P2 square root, and inside bracket this, yeah, please tell me, 1 plus, and this whole power will be 1 by 2. Okay, so this is, sorry, this is Vp by A2. Okay, so this is Vp by A2. Now so from this final thing, if I only calculate value of Vp, so Vp value will be equal to, from here Vp will be equal to W times 1 minus rho 1 by rho 2. So if I only calculate the value of Vp, that comes out to be A1 by gamma into P2 by P1 minus 1 square root of 2 gamma by gamma plus 1 divided by P2 by P1 plus gamma minus 1 by gamma plus 1. So this is another important relation. So because we are saying that we have a shock wave. So when a shock wave is moving, how much velocity it is imparting to the fluid medium through which it has passed. So that also we are now able to calculate. So that is becoming a function of P2 by P1. So P2 by P1 is important because it governs the strength of the shock wave. Second parameter is gamma. Gamma is specific to a fluid medium. And third important parameter is A1, where A1 is speed of sound in the upstream, that stagnant fluid medium through which actually shock wave is passing and then imparting the mass motion. Okay, this is one point. Now another important point is we also must be able to predict that how much maximum value of Vp a shock wave, a moving shock wave, can impart to a stagnant fluid medium. Okay, so to do so, what we can do, we can first consider a shock wave of infinite strength. Okay, so if I consider a shock wave of high strength, infinite strength, so it means in that case what will be happening, my P2 by P1 will approach to infinity, a very large value. So if I take limiting case of P2 by P1 approaching to infinity, and corresponding to that if I calculate Vp by A2, so Vp by A2, I have given you the formulation here. Okay, so if I calculate this Vp by A2, particularly for a limiting case of P2 by P1 approaching to infinity, we get the value equal to square root of 2 upon gamma into gamma minus 1. Okay, and if you do calculate this value, it comes out to be 1.89. Okay, for air at standard atmospheric conditions where gamma is equal to 1.4, by substituting gamma equal to 1.4, you will be able to get that Vp by A2 at max for a shock wave of infinite strength can be equal to 1.89. So the meaning is that, what is Vp by A2 definition? Vp by A2 is nothing but identical to flow Mach number. Okay, flow Mach number of the downstream fluid, because Vp is velocity of the downstream fluid and A2 is corresponding speed of sound. So Vp by A2, as it is becoming identical to that of the Mach number of the downstream fluid. So the meaning is that if a shock wave of infinite strength moves through a fluid medium, that fluid medium with the Mach number of 1.89 will move towards the shock wave. So it means that behind the shock wave, behind a moving shock wave, you can have a supersonic flow situation. Okay, so if say through some stagnant fluid medium, just a wave has moved, so that can create velocity identical to that of supersonic flow situations. Okay, so now we will stop at this point and then we will discuss further in the next.